So we have just a little bbit more information to learn before the end of the semester. And it was the last half of 5.6 in your book. And we're looking at area between a curve and area bounded between two curves. We've looked at definite integrals and what that means, being symmetric, I was going to say definite integrals as area, but they actually take into account area under the curves as being negative. And so if we're just looking at a definite integral, we're looking at the net area. So it's taking the area in consideration of the area above minus this area below plus this. And so it's going to be net area. So now let's just look at these two graphs. And I also want you guys to remember some things that you've learned back in algebra. So remember that two functions are even. By definition, if we can plug in a negative value for x in our function, so if we look at f of negative x, this gives us back the same thing as our original function f of x. So changing our x value does not change the y value. So you can see that in this graph A, that this is an even function. So if we wanted to find the area of an even function that's continuous between the bounds negative a and a, really all we would have to do is find the area from 0 to a and then just double it, because it's the same area on the left between negative a and 0 as it is from 0 to a. And so this is what this theorem 8 says from our book. Let f be a continuous on a symmetric interval negative a to a. If f is an even function, then we can say that the integral from negative a to a of f of x dx is the same thing as looking at 2 times the integral from 0 to a of f of x dx. Recall to be an odd function. That meant that if we plugged in negative x wherever we saw an x and a negative y wherever we saw a y, then that would give us the original function. So negative f of negative x equals our original function f of x. So basically, if I plug in this value in here of x, this is my y value. If I change them, I'm going to get the same thing. So this is negative x. Notice that, and this is y here. And this here would be negative y. So anyways, if this is an odd function, and this is symmetric across the origin. So think of it as if you folded your paper along the x-axis and then the y-axis or vice versa, the graph would lay on top of each other. If it's an odd function, then we can say that the integral from negative a to a of f of x dx is equal to 0. Okay, so those are just some tools that can help us if we want to remember them when we're looking at finding definite integrals. So let's look at an example really quickly, which says that we're going to find y, we're going to find the integral of y equals x times 4 minus x squared on the interval from negative 2 to 2. Okay, so we're going to find the definite integral. So if we want to use that fact, we can look and see if this is an even or an odd function, because these values here, -2 to 2, that's a symmetrical across that origin, or across the y-axis. So if we look at f of -x, and let's call f of x this function we had, or I could call it y of x if we wanted to. That's where function notation is nice. So if we go back in here and we plug in -x, wherever we see an x in this function, we would get back -x square root of 4 minus, and then we're squaring the -x. And so this is the same thing as -x square root of 4 minus, well, -x quantity squared is +x squared. That's not the same as our original. So it's not even. But notice that it's just off by a negative sign. And so notice that that is the same thing as negative f of x. So negative f of x equals f of -x. So it's an odd function. Well, if this is an odd function, that told us that the integral from -2 to 2, that definite integral, was equal to 0. And so if you wanted to do that on an exam, you could, but you would have to explain why you got that that was equal to 0, because f of x is an odd function. Okay, so let's actually, I want to kind of look at this too. Let's say that we didn't notice that this was an odd function and we wanted to take the definite integral. Let's take the definite integral from -2 of 2 of x times that square root of 4 minus x squared dx. And let's show that we get 0 back. And that will be a good review, because in that definite integral, in order to solve it, we're going to have to use substitution. So we want to find, without using what we just did, -2 to 2 of x, the integral of that, of x times 4 minus x squared dx. Okay, so this is not in the form that we can just go ahead and integrate, and it's not in a form that we could rewrite it without that radical and distribute. And so this is where we need to use our substitution. And so we talked about different ways of what we should choose to be our value of u, which is usually what we choose to be, what our substitution is. And it's something that when we take the derivative of, will cancel out any other x in that function. Another way to think of it is, tricks to think of it is, if there's more than one term underneath the radical, that's what you're going to choose. You have some parentheses with multiple terms in there, that's what you're going to choose. Or if you have something in the denominator, you choose that. Any power of e, you choose that a lot of times. Or natural logs. We don't know how to integrate natural logs, so that's a good thing, but we know how to differentiate natural logs, so logs work. Okay, so in this case, we're going to choose u to be our 4 minus x squared. Once we chose u, recall we took the derivative of both sides. So derivative of u is 1 du equals derivative of 4 minus x squared is -2x dx. This is where we went in and we went back in and substituted in our value of u, and we needed to substitute in dx. So in this over here, we solved for dx, and we could do that by dividing both sides by negative 2x. So we get dx equals du over negative 2x. If you put back in your bounds, let's put what variable they represent. Right now I have x is equal to negative 2 and x is equal to 2. Of x square root, well, what I had chosen my u to be was the radicand, so I'm just going to put square root of u. And then dx, well, dx was this du over negative 2x. So if everything goes well, which it did, we can cancel out any of the variables x left in our integrand. And so notice that we have an x over here and up in the numerator and this x in the denominator, and they cancel out. We can always pull out any coefficients in front. And so notice we have this negative 2 in the denominator, and all we have in the numerator is this 1, a 1. So we can pull out a coefficient of negative 1/2. Integral. I think it's easier if we change our bounds now in terms of u, so we don't have to go back and do our substitution and then do it. So let's rewrite square root of u as u to the 1/2 power to help us take the antiderivative of du. So all we're going to do is to figure out what our bounds are in terms of u instead of x. We're going to go in and we're going to plug in what is x equals negative 2. So if we go in here and we plug in negative 2 wherever we see an x, we would get in here u equals 4 minus negative 2 squared. Well, negative 2 squared is also 4. And so 4 minus 4 gives us a value of u is equal to 0. So when x was negative 2, u is 0. So do the same thing here when x is positive 2. Well, notice if you plug in the same thing there, we're going to get the same thing. We're going to get u is equal to 0. So I don't know if you guys remember, but that was another property that we had for definite integrals. If we had the bound or integration and our bounds were the same on the top and the bottom, this is equal to 0. Okay, well, we can use that. But let's say we didn't change our bounds, just so we can get to this integration. And I kind of want to talk about this. Anyways, let's say we didn't change our bounds. So with bounds changed, we got 0 to 0 of the negative 1/2 times the square root, the integral from 0 to 0 of u to 1/2 du. If we didn't change our bounds, we would keep them with x equals, just so we remind ourselves that we need to go back in here later. X equals negative 2 and x equals 2. So let's bring down our coefficient that was in front, negative 1/2. And now let's take the antiderivative of u to the 1/2 power. So if we added 1 to the 1/2 power, we get 1/2 plus 2/2 is 3/2. And now we're dividing by our new power. We're dividing by 3/2, but instead of dividing by a fraction, let's think of dividing by that fraction by multiplying by the reciprocal. So instead of dividing by 3/2, let's think of it as multiplying by 2/3. And we're looking at this when x equals negative 2 to x equals 2. So I would clean this up a little bit. And because in this case, I did not change bounds, I kept my x values as the bounds of my integral, I would have to go back in and I need to choose and replace what u is. But I notice here when my coefficients, I have a 2 in the numerator, denominator cancels. So here I have this coefficient of -1/3. Let's rewrite this as a radical as we're doing this. So this is a square root. And let's put u under here. U, recall, was, stop doing that. U, recall, was 4 minus x squared. And then we're going to cube it. And these are our bounds again from x equals -2 to 2. So recall, we're plugging in our upper bound to our antiderivative minus our lower bound. So this is equal to -1/3, that outside the bracket, of the square root of 4 minus upper bound first, 2 squared, and that quantity is cubed, minus, now plugging in the lower bound, so the square root of 4 minus -2 squared cubed. No matter how we look at this, with all those different rules and going on all the way out and plugging in values, which hopefully we could have saved our time from doing that, we get some number here, which is 4 minus 4 underneath the radical is 0, squared is 0 is 0, 0 cubed is 0, so -0. Anything times 0 is 0, which is the same answer that we had gotten before and knew that we should get when we did all the algebra. Okay, so recall definite area can represent, I'm sorry, not definite area, definite integration can represent area bounded between the x-axis and the curve. Well, we're getting 0 here, and that's telling me area when I'm between -2 and 2 of that is not going to give me back 0. Really what we got back here was the net area. So it's basically the area above minus the area below. Let's say now it's asking us, let's find that area bounded between the x-axis and the y-axis. We can come back here later because we did a lot of our work already from the integration and finding the antiderivative. Actually, let's just go over here. And we found our antiderivative was equal to this piece. So -1/3 square root of 4 minus x squared and that quantity cubed. If you're trying to find the area bounded between the x-axis and this curve, and I meant to put in between x equals -2 and 2, and I was writing this out. We always need to check to see if our function crosses the x-axis. And if it crosses the x-axis, we need to see which piece falls below the x-axis and which piece is above the x-axis. And normally we split this up into 2 separate integrals, and we take the part above the x-axis plus the absolute value of the part below the x-axis. And so we need to find any x-intercepts. So area beneath the curve, first thing that you want to do, if you want to first find symmetry, that could help too. So, but we want to find x-intercepts. And that's when our value of y is 0. So we get 0 is equal to x square root of 4 minus x squared. Well, this is already factored, so I can look at this is when x equals 0, and it's when the square root of 4 minus x squared equals 0. I can't just take the square root of both of those terms because of the subtraction in between. If that was a single term, we could do that. But I can square both sides. So I get 4 minus x squared equals 0. And this is a difference of squares, so I could factor this 2 minus x, 2 plus x equals 0. And 2 minus x is 0 when x is 2. And 2 plus x is 0 when x is negative 2. Technically, because I squared both sides of my equation, recall that that could give me an extraneous solution. And so technically I should go back in and check to make sure that those values set this equal to 0. And I can see that they do. So once you find out what your x-intercepts are, you need to find out if any of these x-intercepts fall between this negative 2 and 2, the bounds of our integration. And 0 does fall in between there. And so we know that we're going to have to split up our integration. Let me just call this f of x. It just makes life easier. So we're going to split up our integration of f of x from negative 2 to 2 dx. And this was equal to negative 2 to 0 of f of x dx. Plus the integration from 0 to 2 f of x dx. Well, we know the area above the curve and below the curve are the exact same number from knowing that this is either odd, and we have the same distance from that x value and the y-axis. So we also know that this is the same thing as twice the area of one of these, right? So we could also write it as the integral, 2 times the integral from 0 to 2 of f of x dx. Okay, well, we had already done a lot of this work before. And so that work that we had done before, this is 2 times the antiderivative. And our antiderivative, we said, was actually, hold on. Okay, so I just wanted to take a minute and make sure I wasn't doing anything wrong. And we looked at the graph of this and we saw that the piece from 0 to negative 2 was below the x-axis. And so really we could just take the absolute value of this piece plus the piece above the x-axis, which is 0 to 2, which again, we know would be twice this value. We also discussed that if we didn't know which piece was above or below the x-axis, we could basically take, but we knew that it touched or crossed the x-axis at some point, that we could just take the sum of the absolute value of each interval. And that would also work. But because look at this, and this was above the x-axis, when I take the antiderivative of this f of x and evaluate it from 0 to 2, I should be getting back a positive number. And so we had already found what the antiderivative was, and we found that that antiderivative, I'm just going to pull it down, is this piece here from previously. And so we're just going to evaluate this integral at our bounds from 0 to 2. Hold on. from 0 to 2. And so let's go back in and let's plug in 2. So we had this 2 out front in here times the integral. Now plugging in our 2 value of -1/3 square root of 4 minus, and then we're going to plug in the 2. We're going to square it, minus -1/3 square root of 4 minus, now we're going to plug in our lower bound, 0 squared. So this is equal to 2 all times -1/3 times 4 minus 4 underneath the radical gives us the square root of 0, which is 0, minus a negative, so we really get plus 1/3. And this is square root of 4, which is 2. So we get 2 times 2/3, which is the same thing as 4/3. So the area bounded between those two curves is 4/3. It's only bounded between, actually, you could think of the x-axis as a curve, but bounded between that curve f of x and the x-axis, adding the areas above and below, we get 4/3. I just want to pull up really quickly for those of you watching the video the picture of this graph that we were just finding the area beneath. And you can see that piece above is between, the graph is above, f of x above the x-axis between 0 and 2. You can see that this is a graph that looks symmetrical across the origin, and then we just took the absolute value of the piece below, or 2 times the area from 0 to 2. Now we're going to look at finding area bounded between two curves or more. And so that brings us to the following picture. And so if we're looking at finding the area bounded between f of x and g of x, first thing that you have to figure out is which function is bigger than the other function. What y value of the function is bigger than the y values of the other function in between the values that we're trying to find the area of. And so if we're trying to find the area from a to b, notice that this function of f of x in this picture, those y values are bigger than the function of g of x between x equals a and x equals b. So notice that if we look at the integral from a to b of our function f of x dx, and because this is strictly above the x-axis, we don't have to worry about anything, that would give us this area, the fundamental theorem of calculus, between a and b. And if we looked at the integral from a to b of g of x dx, that would give us this area below g of x and the x-axis. Well, notice if we subtracted off that area of g of x in there, that would just give us the area that we wanted. And so if we look at the area of our upper function minus the area of our bottom function, that would give us the area bounded between those two curves. So a couple stipulations that we have to put on there, that we have to assume that, or we don't have to assume, we need to know that our functions f and g are continuous on that interval AB, and we need to know which function is bigger. So the function that is bigger is the one that goes first minus the function that is smaller on AB. Then the area of the curves between f of x and g of x on AB is given by the antiderivative, or definite integral from a to b of our function f of x minus our function g of x. So let's look at a few examples. Okay, so we're given an example, we're given a graph of some function y equals, it looks like x squared is our function, that's that parabola shape in here. And we want to find the area bounded between that and the function y equals x to the fourth minus 2x. And so we're trying to find that area bounded between those two curves. And so we need to look at which is our top function and which is our bottom function. And we're going to look at the bounds of the integration. Looking at this, I have x equals -2 to x equals 2. My upper function is the 2x squared minus my bottom function. So because there's more than one term in my bottom function, you need to be careful. I need to put brackets or parentheses around that. So minus the whole function, x to the fourth minus 2x squared. And then this variable is in terms of x, so dx. So we can distribute this negative and combine like terms, and we can rewrite this as the integral from -2 to 2 of, well, this is going to give me 2x squared, and this is now going to be positive 2x squared. So this would be a 4x squared minus x to the fourth dx. Well, we were just talking about symmetry and using symmetry to help us to find area. And so we could technically use that. Notice our bounds are symmetrical across the y-axis. Our bounds are -2 to 2. And notice that this picture is symmetrical. Let's just show. Let's call it f of x. F of x equals 4x squared minus x to the fourth is even. If it's even, then we can just look at 2 times the area from 0 to 2. And we can show that's even because f of x, if I plug in -x wherever I see an x and I raise it to an even power, that's going to become positive. So f of -x is the same thing as f of x. So we could, if we wanted to, say because it's even, because the integrand is even, this here is 2 times the integral from 0 to 2 of 4x squared minus x to the fourth dx. Either way, you don't have to do that. You could have just done it with our bounds from -2 to 2, and you'll get the same result. So let's go through here. This one isn't bad to take the antiderivative of each term. So we have 2 all times the antiderivative of 4x squared, that is 4x cubed over 3, add 1 to our exponent, divide by our new exponent, minus the antiderivative of x to the fourth, adding 1 to our exponent and dividing by our new exponent is x to the fifth over 5. And we're evaluating this from 0 to 2. So we can go in here, we can plug in our upper bound wherever we see an x. So we have 4 times 2 cubed all over 3 minus 2 to the fifth all over 5 minus, well, if we go in here and we plug in 0 wherever we see an x, 0 minus 0 is 0. So minus 0. So let's kind of clean this up. So we have 2 all times, well, 2 cubed is 8. And 8 times the 4 out front, that gives me 32 all over 3 minus 2 to the 5th is 32 all over 5. I need a common denominator. I can see my common denominator is 15. So let's just multiply this 32 thirds by 5 over 5. And this 32 fifths by 3 over 3. So we need 2. 5 times 32, that is 160 thirds, 15ths, I mean. Minus 3 times 32, which is 96 15ths. So 160 minus 96, that's going to give me 64 15ths. Or that's 128 15ths. Fifteen goes into 128 8 times. So it's 8 and 8 15ths. So that total area should give us 8 and 8 15ths squared units, whatever that is, whatever units it's in terms of. Any questions on that? So we have another picture in front of us, and we're trying to find the area bounded between these curves. We're given that one curve is y equals x. We're given one curve as y equals 1, and we're given one curve as y equals x squared over 4. And so notice that there's two pieces in here that we have to worry about, because there's different pieces of which functions on top and which functions on the bottom. And so let's look at this between 0 and 1. Notice that this function here is our function of x. That's our top function, the one that's bigger y values. And notice that the function below that is this y equals x squared over 4. And so if I break down this integral in here, well, if I'm looking at the area, that area of the integral that's bounded between the x value of 0 and 1, my upper function, the one that is bigger y values, is x minus my curve below, which is this x squared all over 4. Parentheses around that, dx. And then we're going to add the area over here. And that area over here, notice that our function y equals x is not what's the upper bound of that area. This is y equals 1. And so we're looking at the integral. Our x value we're starting is at 1 to the x value where we're ending, which is 2. Our upper function in this case is 1 minus the lower function. Well, the lower function in this case is the same thing as the lower function for the other integral that we used. So it's x squared over 4 dx. And so we can find the area by breaking that down and looking at those definite integrals and summing them. And so let's go ahead and do that. So the antiderivative of x is x squared over 2 minus the antiderivative of x squared over 4. Well, that's x cubed all over 3, well, times this 4 also is 12. And this is all evaluated from 0 to 1. Plus, taking the antiderivative of 1, we get x minus the antiderivative of x squared over 4. It's x cubed over 12. We're evaluating this piece from 1 to 2. So plugging in our upper bound first, we get 1 squared is 1, and 1 over 2 is 1/2, minus 1 cubed, which is 1, all over 12. Now plugging in 0, I notice I don't have to worry about putting in parentheses because 0 squared over 2 minus 0 cubed over 12 is 0. Plus, so upper bound in this case is 2. Plugging that in wherever I see an x, I got 2 minus 2 cubed is 8 over 12. Now I have to be a little bit careful because when I plug in 1, I am going to have a value more than one term. So plugging in 1 wherever I see an x, I get 1 minus 1 cubed is 1 all over 12. We can distribute, we can then combine like terms. So we have 1/2, well, they're all like terms. Maybe things with the same denominator. So we have 1/2 minus 1/12 plus 2 minus 8/12. This is going to give me a -1 plus a 1/12. So I notice my -1/12 plus my 1/12 cancels. Let's just look at our whole or integers. 2 minus 1 is 1. And then I have a plus 1/2 minus an 8/12. So I need a common denominator, which is 12. So I have 12/12 plus, that's going to give me 6/12 minus 8/12. So that's 18/12 minus 8/12 is 10/12. Reduce that, 2 goes into both, I get 5/6 units squared. Sometimes though, and you guys will see this next semester when you're taking Calc 2 about integration. So sometimes it's helpful to integrate with respect to y instead of x. So what this theorem says, or what this says is, if we're trying to integrate with respect to y, if the region bounded curves are described by a function of y, the approximating rectangles are horizontal instead of vertical. Basic formula has y in place of x for these regions. And so noticing here that we're basically the x value that is larger is on top minus when the x values are smaller. And we're going to look at our f of y value minus our g of y value. But instead of using your x value of integrations, we're going to use the y value. The bottom bound is c, and the upper bound is t. So in that problem that we had just done, it probably would have been easier, or it could be easier, to integrate just once. Don't have to split it up into 2 different sums of integrals. Notice that I can look at this function and doing it this way. That's my upper function minus my lower function, which is this. But because it would be in terms of y, well, this function x is already in terms of y, x equals y. I just need to do a little bit of manipulation in this case. I need to rewrite this in terms of x in terms of y. So rewrite x in terms of y. So let's solve for x really quickly. So let's multiply both sides by 4. And we get x squared equals 4y. Take the square root of both sides. I get x equals plus or minus, but I noticed that I'm looking at the values over here on the first quadrant. So I'm just going to look at the square root of 4, which is 2, square root of y. I'm going to write that as y to the 1/2 power, just to make my life a little bit easier. So I notice my upper function is this 2y to the 1/2. So we'll look at the integral of this 2y to the 1/2 minus the lower function, which is y. And then I'm doing this in terms of y, so dy. And my bounds on my y value are 0 to 1. So when we take and find the area of this, we should get back the same thing we got for the area when we did this in terms of x, which was 5, 6. Okay, so this isn't too bad to take the antiderivative of. So 2y to the 1/2, adding 1 to my exponent gives me 3/2. Divide by 3/2 is the same thing as multiplying by the reciprocal, which is 2/3. Minus the antiderivative of y is y squared over 2, evaluated from 0 to 1. So I'm just going to clean this up. 2/3 times this 2, that's 4/3. Y to the 3/2, it doesn't matter in changing that in terms of radical because I'm only evaluating at 1 and 0. If it was other numbers, I would probably rewrite that as a radical. So y to the 3/2 minus y squared over 2, 0 to 1. So if we go in here, wherever we see y, we place it with our upper bound of 1. We get this 4/3 times 1 to the 3/2, which is just 1, minus plugging in 1 and squaring it, we get minus 1/2. And so we want to get a common denominator, which is 6. And so getting a common denominator, and actually, I'm sorry, minus, but plugging in 0 in here would give us 0. So that's why I skipped that. We'll get our common denominator of 6. We get 2 over 2, which is 8/6, minus 3/6, which is equal to 5/6. So here's a case where it would have been a lot easier to integrate with respect to y. Notice how much faster that took us, not too bad, instead of x. Okay, so one more example. We have x equals 2 times y squared, and we're looking at the area bounded of this with x equals 0 and y equals 3. So we can look at this, x equals 0, that I know is the x-axis. Y equals 3, I know that that is a horizontal line at 3. And the curve x equals 2y squared. So I can keep this in terms of y and maybe bound this, but or we can change this in terms of x, and that's up to you. If we keep this in terms of like this, basically just go opposite if you want to. Logging in points is not going to be too bad. And so let's plug in values for y. So if we let y equals 0, if y is 0, 2 times 0 squared, x is 0. So I have a point here at 0, 0. If I have y is 1, my x value that I get back is 1 squared is 1 times 2 is 2. So I have a point at 2, 1. And if I plug in, well, I notice let's plug in 2. If I plug in 2 here, I get 2 squared is 4. 4 times 2 is 8. So we have a point here at 8, 2. And this is not going to be to scale. So basically, we need to figure out what x value is going to give us back y equals 3. Well, if we plug in 3, we get 3 squared, right, is 9. That's what we want. You know, y equals 3. So y equals 3, we get 3 squared is 9 times 2 is 18. Okay, so way out here. Same as way out here. So notice which curves we're looking at. We're looking at this y equals 3 is the top, and this function here is the bottom. We're trying to find this area in here. So we can keep this in terms of y, or we can change this in terms of x, and that's up to you. So if you think of it as rectangles and keeping it in terms of y, you can see which function is on top and which one is the bottom. The bottom one here is this x equals 0. And the top one is this 2y, x equals 2y squared. And so if we kept it in terms of y, our integration, our bounds are 0 to 3. Our top function, the bigger one, is 2y squared minus this bottom one, which is 0 dy. And so taking the antiderivative again isn't too bad. Looking at that, we would add 1 to our exponent. So we would get 2y cubed over 3 divided by that new exponent. We're evaluating this from 0 to 3. If we plug in 3 there, wherever we see a y, we would get 2 times 3 cubed over 3 minus 0. So that's the same thing as 2 times 3 squared, which would give us back 18. If we had changed it, we would have had to change things in terms of x instead of y. And thinking of it as rectangles, my upper function would have been y equals 3. And my bottom function here would have been, I would have had to, again, change this. So it would have been x squared. Actually, no, I would have taken the square root. It would have been y equals the square root of x over 2. My bounds that I would have used, my upper one is 3 minus my bottom, probably would write it as x over 2, the 1/2. And my bounds for x in that case would have been 0. And here it would have been 18. So if you integrate that dx, you should get the same thing of this. But we're out of time. So I'm going to just pause for a second and let's see if there's any questions.